Right, hello. Welcome to Hacking Kubernetes live demo marathon. I'm Andy from Control Plane. We are cloud-native security engineers, lifetime hardened, wizened consultants. I've done various things, as well as being a very proud CEO of 50 people across New Zealand, North America, and the UK, and Europe in general. Also do work in the Cloud Native Computing Foundation's Technical Advisory Group for Security. This is the parent organization under which Kubernetes and or Containerd from Docker and Prometheus, and these kind of cloud-native technologies all sit. The Technical Advisory Group performs security assurance on new projects joining the CNCF and keeps us at the bleeding edge of cloud security. Purely community contribution and voluntarily based. Please do stop by the Git repo and have a look if you are interested. Very nice, friendly people. We've just launched a new conference as well. If anybody finds himself in Seattle in the cold month of February, we'll be running Cloud Native Security Con for 2 days there with a number of luminaries running the thing, including Liz Rice, who some of you may recall from the original container security days. And finally, Open UK is a pressure group into the UK government trying to get open source maintainers paid to fix security problems and patches. Various other things. I wrote a book, Hacking Kubernetes. The first half of that book is available. I wrote a SANS course. You can download the first half of the book, and there is my esteemed co-author, Mr. Michael Hausenblas, for free behind an email capture wall at controlplane.io. This is basically the book, the talk of the book. These are the things that we do. We are working with regulated industries and banks in New Zealand and looking to start working in Australia as well. We are nice people, and I promise interesting work. With that, what are we going to do today? We'll start off with some threat models. What are we actually going to do to hack Kubernetes? Then, of course, the supply chain is so hot right now. We will get into ultimately trying to pwn a cloud account from a supply chain attack. So we'll start with the supply chain, we'll pop a reverse shell, we'll do a container breakout, which is, as you've seen already, is the dirty pipe. This is a kernel vulnerability. We'll exploit it from inside Docker or Run C specifically. Actually, Containerd, he says. We'll then try and enumerate a kubelet host, and finally try and take over the cloud account with that errant banana. Onwards, there are many people that I have to thank for standing on the shoulders of. Some of these are other demos that I've done. This is what happens when Kubernetes lands in an organization. We have an archetypal adversary, the dread pirate, Captain Hashjack. He wants to get all up in your clusters and crypto lock things or run his own workloads. We will model our defenses against him as an attacker. This is my penetration testing treasure map that I use on engagements. This is, of course, in the book as well, and enumerates the things that we look for when attacking a container. Of course, containers are just microcosms of Linux. There is nothing out of the ordinary, except for things like specific things that are injected, some of the behaviors of the runtimes. Some things are slightly different in containers, but as always, we don't want to run things as roots, and we look to escalate privilege to root in a container because almost all container breakouts have that prerequisite. They require you to be root or have a suite of root capabilities to attack further things. Okay, so first we do adversarial modeling when we're looking at defending a cluster. The reason we do this is because defending against the NSA versus being Valve and trying to stop kids from dumping your source code, I guess. Very different threat models, very different capabilities in terms of the adversarial nature of these adversaries. So this is the default adversary matrix that Control Plane use on our threat modeling, penetration testing engagements. I'll zoom through quickly. At the top, we have script kiddies. Minimum viable cloud native security is not shipping CVEs to production, because if you can spin up backtrack Kali and Metasploit, then it's professionally negligent of a defender to offer that sort of lowest hanging of fruits to somebody who's just reusing tools. Then we get into motivated individuals, maybe slightly greater capabilities there, as you see, maybe able to actually chain things together. Insiders, well, at the point we get to insiders, we have to rely upon sufficient segregation of duty internally. While DevOps at large and DevSecOps encourage freedom of access and contribution, trust but verify, etc., etc. Then we get to organized crime. This is where the dread pirate Captain Hashjack sits. State-affiliated terrorist groups, APTs, we've seen things like Fancy Bear make a bit of a splash over the past 12 months or so. Why are these organizations dangerous? Because they're state-sponsored, and therefore they have the capabilities, the ways and means, and the financial backing, often bouncing through places like Switzerland, that allows them to perform these attacks on behalf of a state, let's say. What we've seen, for example, with the Ukraine invasion, is that we expected Russia's attacks on things like the Colonial Pipeline and various other crypto locking attacks on US government departments or localized departments. We expected everything to burn. We thought this would be a highly targeted capability, and actually the sort of new cyber warfare revolution would have arrived over the past 12 months or so. Transpires that's not the case. There is no Stuxnet level of zero-day chaining. It's very much spray and pray, which is good for those of us on this particular side of the conflict. But the point there is with these groups, we look to just elevate ourselves sufficiently high above the average, because when these drive-by attacks are going on, while the capabilities and the financial backing are there to target specific organizations, if we are hardened to a sufficient level that actually there are less well-defended and therefore more appealing targets, we're likely to maintain the sanctity of our infrastructure. Moving up, we get to cloud service insiders. This really sucks. This is looking at things like the Capital One breach, where an individual out of Seattle used privileged information about AWS customer IDs. They were also aware that there was a server-side request forgery on the AWS WAF. They were also able to determine, either inside or outside, probably again using that internal knowledge, that there were loose IAM permissions on the role used for the WAF, and dump all of Capital One's customer data, Capital One being the poster child for cloud security. Finally, foreign intelligence services. At this point, there is the risk of physical threat or harm, at which stage, sort of speaking personally for the organization that I'm involved with, the reliance is upon controls at lower levels to be sufficient, that I can't be coerced into something. There are multiple layers, and I don't have backdoor keys to anything. But of course, it is very difficult to fully defend against all of these things, so a layered approach and quantification for the controls comes with attack trees. Before we get to those, the reason this is so difficult is because as an attacker, as we know, all we need is 1 foot in the door, 1 chink in the armor, and then we can pivot and attack the visible horizon. As a defender, the checklists are endless, and this is why automated tooling and cloud native, yada yada, I won't go on about it too much. The way that we attempt to denormalize the complexity into one place is with attack trees. So we're building our threat models, we've identified our adversaries, we have ideated on what could possibly go wrong. Then we build something like this, which says these are all the negative outcomes we can build for a system. Control Plane built these for the financial services user group and threat model Kubernetes 4 or 5 years ago. We then take these graphs, or trees rather, and apply cross-cutting controls over multiple branches at once. Why am I going on about this? Because ultimately, any sort of defense built for a system has to stand up to the rigors of time and future maintenance. And when somebody comes to maintain a system or build a new feature or apply a new control, and there is no paper trail back to why specific controls were implemented, systems get loose and are likely to introduce vulnerabilities because it's hard to quantify or justify why a control exists. So, love these things very dearly, wrote a course for O'Reilly, it's all open source and free, it's on our GitHub. With that, let's get into attacking some things. Could I possibly have a glass of water, please? Right, don't panic, the demo marathon is commencing. I'm sure that we know most of these MITRE-related things, thank you very much. But on the left-hand side, we have something straight from the Kubernetes docs. These are the 4 C's of Kubernetes security. First of all, we start with the code. From a container or a Kubernetes perspective, the code is our application code. It's all the dependencies that come with it, bundled up into a tarball, and that is an OCI container image. That's what we distribute. The code wants to change regularly. It's where we deliver features. It's where we do better than our competitors in terms of what we are selling as a product, as a software product. And it's likely to have vulnerabilities because we don't assure every single line of code that goes through, even with pull requests, 4 eyes on everything. It's likely to have vulnerabilities. This is because at one extreme of the spectrum, we can move very slowly and formally assure everything. I use air burners around the formality. Or we can have just continuously integrate to master and ship stuff as fast as possible. So control plane models all application code as already compromised, because this then affects the topologies and defensive controls that we can then apply. The code sits in a container. The container is a runtime instantiation of the code. We're thinking almost object-oriented instantiation. One or many instances of that code. Around the container, we then have our namespaces. So the most important being the process namespace, because that isolates the process from being able to see other things on the host. But of course, we have namespaces for the process also includes memory, of course. We have mount namespaces for what is on disk. We have network namespaces so that there's a semblance of isolation. All of these things are the kernel drawing a window around the process and saying, you can only see what I paint onto the window. A normal system, an unnamespaced root system, or the root namespace, looks through the window and sees everything. It can observe everything, because that's how Linux is built. But namespaces just start to paint stuff on the other side of the window to give the false impression to the process that it is the special only process running on the host. So the container is also somewhere we can hang Linux security modules. It's where we can apply other layers of capabilities, capability dropping, namespaces, our C groups, which are just control groups for resource accounting. That then is the atomic unit of Kubernetes deployment, containers in a pod. Outside of that, we have the cluster. The cluster provides us with namespacing, service discovery, network mounting, so we can deal with things across different nodes via a virtual encapsulated, generally container network interface. We also get our volumes in here, where we deal with storage and other cross-cutting cluster concerns. Finally, those things all sit somewhere. Everything here, while virtual in some sense, is also specifically anchored in hardware somewhere. So it's not like a virtual machine where we have hardware interrupts being caught, but it is very much a single Linux kernel starting processes on a running kernel as opposed to a virtual machine, which is doing a full BIOS simulation, booting PID1, emulating a disk seek to boot PID1, all that big, slower, expensive stuff. There is a middle ground. It's at the end of the book, micro VMs. But with that, let's get into the demos. So supply chains, everything is software. Let's do a supply chain attack. We want correct and non-violent code. We don't get that if Bob is able to get between Alice and Charlie and drop malware into the build. This is very much reflections on Trusting Trust's 1984, or 82 presumably, problem. So how do we attack supply chains in this day and age? Well, we can either go straight in for the source code. This is somebody jumping on my machine when I've left it unlocked, or the source repository, that's getting access to either hosted GitHub or maybe the physical infrastructure that Bitbucket or GitLab sits on. The build infrastructure, this is the SolarWinds style attack, where even if you hash every single stage, if somebody can switch a file before it's packaged, that package is a binary transform in some way. I say binary, it's a transform that changes the hash of the artifact. So even if you hash everything that goes in, if you can switch out a single piece of software or a line of code just before it's packaged, that is either being compiled, even just being zipped up, anything that changes the SHA, of course, everything does when you're packaging, then the output will get signed. And this is why code signing is not the panacea that people think it is, because the transformation step is what has to be assured. It's an interesting problem that there are lots of time and effort is being thrown at the moment. We can attack a trusted supplier. So a dependency that the source code pulls in. This is the big problem with dependency graphs. You can go to deps.dev to see how many dependencies, immediate and transitive, are pulled in by your favorite piece of software. Hint, it will be a hell of a lot. The only really safe way to deal with that is to pin every package, and as anybody knows who has tried doing that, there is a compromise there between the amount of time you can spend upgrading things versus the amount of time you spend pulling evergreen software from head or from a package repository without knowing what's in it. Finally, the runtime environment. This is more difficult. So what are we going to do? We will stick malware into an application dependency, attack my end user device, which is this laptop. From npm, the package installer will run some malware, and game over approaches for my local stuff. Okay. What do I want? Not that. Okay, so what have we got here? Okay, so a node module is characterized by this present of a package.json and the content of this directory. Now, this is not sat on the public internet because uploading this to npm would allegedly be unethical. But what we have here, first of all, okay, so what do we see? npm exfil, we've got some scripts. Very politely, the package actually self-identifies itself as malicious. Within the script section, we have two keys. One is test, the other is pre-install. If we could do an npm run test, well, we know that echo is a bash command, and we can see that echo's been executed, or bash or shell. So the contents of that key, of the value is being passed to a shell. In this case, for passing this exfil.sh as a pre-install hook, I'm sure you can imagine what's going to happen. This is kind of like a curl to bash, essentially. It's a Hail Mary, npm install. Notably, some package managers like Golang do not have this capability, but what's just happened is I would have just pulled some code from the internet and run it in my local directory, and anybody who's able to drop code into there, be that via a typo squatting attack or compromising someone's deployment keys or just actually running malicious code, is able to execute their code in the context of my user. Why is that a bad thing? Well, first of all, potentially we could stick a keylogger on there. That defeats any passwords that I've got on my SSH keys that I'm going to steal below. Monero miners would have been cool when this talk was written. Maybe crypto is now actually on its back dead, but we'll see. And then credential theft. Wonderful. So the credentials that I have in my home directory are what I use to push my own code to GitHub. They should have passwords on them. If a keylogger has been installed, that password won't last for much longer. I've got my GPG keys on here. I have a YubiKey rather, because it is a second factor. It needs inserting into the machine, and it can't actually steal anything from here, which is useful. But nevertheless, if those keys had no passwords on them, then that second factor of signing, which is used to say the person in control of this key at the time they signed this thing liked it sufficiently. It's not really much more of a guarantee than that. It's a signal that the person likes it enough to say, I'm going to cryptographically sign metadata about the object, which in this, or in Git's case, would be the SHA-1 of the Merkle tree entry. Okay, but this is even more worrying. Our .aws directory contains cached session credentials, OIDC, OAuth flows, drop a token onto your local machine so that you don't have to do a round trip every time you want to make an API call. You have an expiry there of maybe 1, 12, 24 hours. If somebody has just accessed production infrastructure and that session token is stolen, that is a bad day. So long, thanks for the fish. Okay, so from a supply chain perspective, I've been able to pull some code, steal what's in the user's home directory, what else might be in there, Kubernetes config. So what does that mean in this case? It means we are going to consider what a reverse shell would do here. So if that code fired a reverse shell from my local machine, somebody would have command and control of my local system. Now, actually, I've just dumped everything and stuck it and base64'd it and pushed it to paste bin back in the day, or maybe I've bundled it up into an OCI image and pushed it to the Docker Hub. Maybe I've committed it to GitHub. There's plenty of things that even with correct firewalling around an enterprise network or production system, a lot of the time these kind of endpoints are available. So what is a reverse shell? Well, in this case, we're taking the Dread Pirate Captain Hashjack's black flagged ship and sneaking malicious code into a target library on a public registry, repository like NPM. It could be Maven Central, it could be PyPI, any of those good things. Where trusted producers are pushing legitimate code, one of the sly ways of doing this is called typo squatting, where you have left hyphen pad and left pad without a hyphen. And the developer, in the course of their day-to-day, just goes npm install save left pad with or without. The malicious attacker who's duplicated the name with a typo in is constantly pushing the same code as the legitimate package to the secondary, malicious typo squatted package. So it's undetectable for the developer until such time as they've got 10,000 weekly installs and a little bit of malware gets pushed into the builds. This happened with the event stream. That was not typo squatting, it was just malware pushed into the application repository. And suddenly 20,000 CI servers automatically build the thing, or build it the next time it's around. So it's unfortunately a lot easier than it should be and becoming increasingly more common. So what happens? This malicious code is snuck into a target library, either the library itself or a typo squatted clone. There are various other quite fruity versions of these attacks. CI/CD builds and deploys. It does not detect the malicious code because it doesn't know what the malicious code actually looks like at that point. There is no VirusTotal-esque signature for it. Some patterns are more obvious than others, of course. If that code makes it through whatever static or dynamic analysis the organization has, it will then be bundled into a container, and that container potentially deployed to our production systems, in this case, the deployment front-end container. This is where, at runtime in production, the application behaves normally. It boots as it should, it instantiates, but it also fires a reverse shell. That's in this case, it's an outbound TCP connection to an endpoint that I, as an attacker, control. That's somewhere routable, probably on the public internet. This is done in multiple different ways, but establishing this command and control, I'm sure, as we all know, can be done via TCP, UDP, and DNS. There are fruity ways of doing it with ICMP. It's reasonably difficult to block all of those. As we saw with the Log4Shell vulnerabilities, people are not firewalling egress connections from corporate networks, and we continue to see it. There was just, I can't remember which, a US government department got popped by this. They only announced in the last couple of days, 6 months ago. The point being, the human capital and cost in maintaining allow lists for outbound connections and filtering them properly is a bit higher than we'd like, perhaps. Ideally, it would be a pull request workflow managed by GitOps or automate like Ansible, just some form of automation in there. But most organizations do not do it, as we saw repeatedly and relentlessly. So this attack generally works in most places. All right, so how do we fix this? Well, 2FA for everything, obviously, avoiding plain text credentials, hardware crypto wallets, because the first spate of these kind of attacks, especially the event stream attack, was looking for hot wallets on disk. Again, we're seeing those incentives shift as crypto continues to plummet from lack of regulation. Air gaps are likely to be completely useless for most people who want to do anything at any sort of speed. And signing, as I've said, is not a panacea. It just means that the thing that you were sent is verifiably the thing that the thing you received is verifiably the thing the other person wanted to send via a side channel. Does not attest to the sanctity of the artifact. Okay, supply chain reverse shell. So basically the same thing again here. Captain Hashjack is sneaking his stuff in, but we're going to actually pop a reverse shell. So in this case, we are going to emulate having attacked a piece of production infrastructure. We're trying to run our code out of context in the victim's machine, of course. So very similar, except we're going to do this with an Nginx image that's pushed to the Docker Hub instead of pushing into a CI build. So malicious Nginx image, you can use the Docker scan tool to do this, which basically sets a backdoored LD preload environment variable, which starts the reverse shell, preloads, but the application runs, built into Linux, it's what it's there for. The front-end container will start, fires our payload, which is our reverse shell. Off we go, listening for that with a terminal multiplexer, sat out on the internet, and profit, ideally. We will also do one more thing just to demonstrate what you shouldn't do, which is not run admission control. Kubernetes has this concept of authenticate, authorize, admission control. It's super cool. It's one of my favorite things in the world, genuinely. It's basically deep packet inspection for RESTful requests. So it gives you the ability to perform any arbitrary code, static analysis, dynamic lookup, whatever you want, at admission control time. You can also mutate the request if you want to. This is the fundament of everything's declarative in Kubernetes, of course, so this is the fundament of admission time security for all the API calls that Kubernetes supports. Super cool. It should be available everywhere. What we're going to see here and do is, because we've stolen those deployment credentials, and we can then, via this reverse shell, we're going to set host PID to true and privilege to true. Privilege turns off almost all security in a container, and especially in a Kubernetes. That is turning off all namespaces apart from the process namespace, which we turn on separately. Turns off C groups, grants all capabilities, and disables all Linux security modules. That's SEARMA, seccomp, SE Linux, all that good stuff. We'll then use a legitimate command, which is namespace enter, to jump into proc1 nsmount. That proc virtual file system path is provided to us by the kernel. Proc1, because we're sharing the mount and process namespaces with the host, is actually systemd on the host. So this is a legitimate way of breaking out of a container. So we'll run this backdoor image, we'll fire this reverse shell so we get command and control. We'll catch that reverse shell, and yeah, off we go. The next phase of our attack is on. So, as I mentioned, in order to, where are we exactly? Not, yes. So, in order to catch that shell, there must be a network route from the infrastructure that we're attacking back to where the attacker is standing with, or sat with their terminal multiplexer. For the purposes of this demonstration, I will use the reputable ngrok, which is network port forwarding over the internet. So at the bottom here, we're seeing 4.tcp ngrok.io 11037. That's the routable URL given to me by ngrok, which pushes a local port, which is here, out to the public internet. So this is waiting for a shell to attach. If this was local, this is essentially a Unix pipe. It's just sat open, waiting for something to connect to it. That something will come from up here, which is the deployment that we'll do into Kubernetes itself. It says, oh, that says old. What does it say? I wonder if I've got my versions set up properly. Okay, so happily that deployed very quickly. Okay, so just to show what we're doing there a little bit more slowly. Okay, so we've taken the output of the kube control command as a dry run YAML, which means that it just pumps out a block of YAML. We're using the unsuspiciously named Sublimino hack image. Then we've got while true, do no hangup, bash, and then we're using the dev TCP virtual file system endpoint. This is given to us by bash. It's not there in SH, and that's the IP routing that we got from, it's actually not the one we got from down here, but nevertheless, the routing that we would have got from a different version. Let me just double check what's going on there. I've got a feeling I left the old demo open. So just for the purposes of engineering purity, I'm just going to repeat that to make sure that it's believable. Whoop. Yeah, it doesn't look good, does it? Okay, there we go. So from the top. Right, so as I was saying, okay, that's also, and cat needs killing. Why have I done that? Because I have quite a heavily tooled up bash shell. And if, yeah, let's just try that. And that's in a loop, so let's make sure I close that one instead. Okay, so that's a cleaned up demo. Let's do that again quickly. So, ngrok shell catcher. There we go. So as I was saying, this pumps out that image. What we should see now is 225.14.385 comes up down here. There we go, 14.385. So we've now actually pushed the right image. Does that mean there's still... Okay, we shall see. Right, so this, again, is the open pipe. We write that in. We'll see that come out of this command. There we go, so there's no hang-up. So this has now deployed the image. Okay, so that's actually called back as it was supposed to. We are definitely in the right... Yep. We're in the right place. So what does that mean? It means that we've now got command and control inside a container on someone else's cluster. If we do a process list, because we're sharing the host's network process namespace, we're able to see everything that exists on the host, including container D, which is the runtime of the container itself. So it's almost like an Inception style, peeking outside of the box. The container should not be able to see its parent processes. We shouldn't ever be able to deploy this pod configuration because we can use admission control, specifically the pod security admission controller, to prevent this from happening. But misconfiguration is still the primary cause of cloud failure. So what else can we do? Let's just have a look and see, how can we tell it's a privileged container? Well, because there's so many things mounted into dev. Why does this matter? Let's just do this again quickly. Because if we have a look in a standard container, container runtimes, rather, do something called proc masking. And that means that some of those, again, we've got proc, we've got dev, we've got sys. These are virtual file system endpoints. They don't exist on the file system. The kernel provides them to us for introspection, debugging, mounting, etc., etc. In a container, you don't want to have access to those on the host. And so they are hidden in many cases, as in here. But within a privileged container, he says, then we can see lots of things, loads of loopback adapters, all the other disks. So we know we're in a privileged container, and that means we can run the nsenter command. This is a legitimate command, namespace enter. This allows us to jump into other namespaces. We've already run it once, as we saw, but now we're going to run it for everything. And we can then check the contents of the root of the system, and we see Chrome OS post install. So we're now in the host's file system context, process context, etc. This is only a misconfiguration, though. Let's do this with a kernel breakout. So just to recap, we gained command and control. We're now inside someone's cluster with the ability to execute arbitrary commands. It's not a container escape, it's a process that wants to be free, says the reputable Mr. Brad Giesman. So in the middle, we saw a non-secured pod. This is what we just did. The evil command is not contained when the configuration is insufficient. What we will do now is run an evil command within a theoretically secured container, e.g. one that's not going to give us privilege, not using that double hyphen privilege flag or privilege equals true. We rely upon the kernel for security, naturally. And in the event that there's a kernel vulnerability, as the dirty pipe vulnerability was, then we can no longer rely upon it. There have been a lot of CVEs against containers in the last year. There have also been a hell of a lot of CVEs in general. There's a whole lot of scrutiny now applied to open source software, and often we can't really dispute a CVE as a maintainer, whereas closed source software, they just don't admit anything. So we've seen all these vulnerabilities. Again, the reputable and honorable Chris Nova says containers are not a security boundary because the kernel is not a security boundary. Now, this was very much the flavor from the Ghost, Google internal open source security team. Containers not a security boundary. But then, what is a security boundary? I mean, hypervisors have all been popped. Air gaps can be jumped over with various physical manifestations and tricks. So my contention here is that actually nothing is inherently a security boundary. Nothing can be fully secured. And the point of threat modeling is to understand the data classifications and sensitivity, where we want that data to go, and what level of control we want to apply to it, so we don't leave our developers constricted by an inability to actually ship anything. We aid developer retention by making systems that are justifiable, quantifiable, and maintainable. So, brief side note there, I think we want to be running the latest version of software because it delivers value to our customers, but the side effect of that is a higher risk of exposure to vulnerability. Okay, off the soapbox. So container namespaces, just a quick view. Again, this is all in the book. One thing to note, we are sharing that localhost loopback adapter in Kubernetes pod, and that is a pod configuration, but these are the namespaces that we have in a container. So what is the dirty pipe vulnerability? It is a memory page handling vulnerability that permits the injection of code into root-owned executable memory. So what does that mean? It means if I can drop a malicious implant into that code, it will be executed by the kernel, which thinks that it's running something for root. I can then use that code to, in this case, drop a secondary implant that will fire a reverse shell back into the container. So within the container, I attack the kernel, drop an implant that calls back somewhere that I'm listening inside the container. It's the same reverse shell idea as over the public internet, but instead we're doing it across the local loopback adapter on the same host. So there's a few strange foibles with this attack. One is that it requires no more than 4 kilobytes of injectable payload. Also, we can't patch the first bytes. And yeah, there's various other things here. The fixed versions, as we can see. So credit to my friend and colleague James Cleverly Prance for dropping this exploit about a week after the embargo was lifted. Actually, there was no embargo. The exploit was just dropped. The vulnerability was just dropped. So it was announced, and yeah, he came up with this quite quickly. So what are we going to do? First of all, we are in a VM to maintain and preserve the safety of my host. That is a vulnerable kernel version, and we will, where am I? We'll get into the right place, I think. Okay, so what have we got in here? The way this vulnerability works is we build and run a Docker file, and it breaks out onto the host. So let's have a look at that Docker file. That's not on here, is it? Have a look at the Docker file. So what are we doing? We're starting with Debian. We're installing compilation tools and a few other things. We're removing libseccomp because when it's inside the container, it's going to be used. So we're going to replace it with a patched version. And I'll show you how we compile that patch. We then drop in runc small, which is the small version of runc that we will assemble. That's just the payload. So we drop that down the proc self-exe self-referential symlink, again, in that virtual file system that the kernel provides to us. Then the next time that runc is called, instead of doing anything container-related, it just runs this tiny bit of code which fires this reverse shell back, hooks a bash shell on the host to the endpoint that we're listening to inside the container, and profits. So you may not expect to see a badly written seccomp library in bad something, but there is absolutely nothing in there. That's then used to in dirtypipe.c, which is the actual payload. It's not the payload, that's the actual exploits. Then the payload itself is this runc small, which moves a few things into place. This is my colleague. This is an elf header, just so it's a binary. And this is all we're doing. It's the same reverse shell again, dev TCP virtual file system endpoint. 172.17.0 is the range that the Docker adapter starts issuing addresses on. We've just looked for 2 to 5, hypothetically. And then that's base64 encoded, that's the payload, and that is what is run on the host. Reasonably simple string obfuscation, but it works nevertheless. Okay, so to actually execute this, first of all, let's do a build. Okay, so the build has assembled that code, it's compiled the exploit, and it's building this container. So all we need to do now is run this. Okay, and at the point that we change the window, it will trigger. Okay, let's get that size again. All right, so what's happened is received that connection. We can see we were vagrant before. We're now ID 0, but are we inside or outside the container? Whoops. That certainly doesn't look like a container file system, but what about the current directory that we're in? So this, as I mentioned, everything has to exist with containers virtually, but physically somewhere. When a container starts, the OCI image that it exists in is untarred into a file system location like this. Pivot root system call is kind of cherooting in modern Linux terms. This is the file system location on disk that the container was running from, virtually, if you like. Abstracted away and invisible to the container. But nevertheless, having broken out, this is where we end up. Of course, this is a bad day. We also now have access to the host's namespace, process namespace. We're on the host, in fact. There is no namespace jiggery-pokery here. It is just a straight-up breakout. Okay, so to keep things moving along, whereabouts are we here? Of course, we know we should always be patching. Containers give us an opportunity to move things along quickly, but that includes base images and golden VMs. Immutable infrastructure is good. So we're now hypothetically onto a container host. And at this point, where am I going here? Yes, we're now onto a container host. So this is, for example, sorry, just lining up the next demo. Let's do that. Yeah, we're on a container host. So this is a kubelet, for example. What we see here at the bottom is the kubelet itself, and then at the top, an example of a pod running in Kubernetes. Everything on a host has to be visible to the root user. The root user is omnipotent, they are omniscient, they must be able to debug everything, and because of the way namespaces work from the root namespace, you can see everything that exists in the subordinate child namespaces. This demo is using infrastructure based on the other side of the planet, I realized recently, so it may take just a second to slowly work its way here. Why is this notable? Because the container runtime sets up various things for each pod. You can see we've got the storage, the runtime itself, the container network interface, but we've also got two forms of injection. One is environment variables. As we've spoken about earlier, environment variables are not a good way of putting secrets into a thing. Any user that can get to the process table can see the environment variables for every other application visible on the host. Secondarily, so they leak. Secondarily, if you do a stack trace, you're probably going to dump environment variables as well. That means that all your logging systems have got potentially secrets in them. And tertiarily, there's also, what is the third one? It escapes me temporarily. But yes, nevertheless, environment variables are not the best thing to use. What is the third one? Pull the slide blank. So instead, we prefer to use secrets via config maps. These are injected as tempfs partitions. This seems to be taking a long time to do the thing. I'm just going to try and coerce it gently. Let's try that again. Yeah, so what do we do with tempfs mounts? Instead of putting, the third problem with environment variables, of course, is that as an attacker, we can just script dumping all the environment variables if we get remote code execution, base64 them up, and off they go to paste bin again. So it's a very easy, understood, and commonly scripted for way of just sucking up all the configuration about an application. This is because the Heroku 12-factor app told us to do it, and it's probably the only thing that doesn't really stand the test of time there. So instead, we want to use temp-fs mounts, which are, temp-fs is a virtual file system that makes it look as if you've got a file system on disk, but it actually exists in memory. The dev, oh, we're timed out, interesting. Why might that be? I wonder if I can't SSH on this network. Has anyone tried that? You can't? Yeah. Okay, onto the phone with no reception. I wonder if I've got a VPN that will do this quickly. Okay, we'll see if that resolves. I can't set this demo up anywhere else. Ooh, actually. No, I don't think it has worked. It's timed out trying to resolve. I'll keep on aggressively brutalizing it until maybe it works. So the temp-fs mounts put a virtual file system endpoint and inject it into the container. Now, the purpose of doing this, I wonder if I can, one further idea, which is maybe Mosh will work. So the point of doing this is to, first of all, we can't just drive by a container and dump all the environment variables. So it's slightly more secure. It also means that the file system endpoint can be protected by standard discretionary access control in Linux. And let's just see if that works. Where am I? And that means still questionable, perhaps. And that means that we have a slightly higher level of protection, let's say. From a drive-by attacker looking in places that they would expect, what we can do is also, so we don't get ICMP on this network either, perhaps. What this means is, yes, we can also use an environment variable to point to the file system location. So we're not using hard-coded strings, magic XYZ. We just need to know one environment variable that points us to a file system location, and then we can go and ingest the thing. Now, what we're not going to see here, I think, is actually that being enumerated on disk, but I can show you what it would have looked like by a selection of interesting errors, but okay, let's just do this anyway. So, what we can use is, I take a portable pen testing kit with me whenever I go on engagements, and it has this command in it, k-sequence file system dump. So what are we doing? First of all, this goes into varlib kubelet pods. Again, all pods have a representation on the host. That is not only their file system, it's also their configuration. Volumes Kubernetes IO tilde star is looking for bound or projected volumes that exist either to statically hold data or to rotate data underneath a pod. And then we're looking through everything in there for files with the names, namespace token or ca.cert. Those are, the ca cert is the public, what happened there, I wonder? Connection times out to 22. Why did I retry that, I wonder? Oh, that was a different host. I don't think Mosh worked either. The point being is, namespace token and ca cert provide the key material and credentials to access the Kubernetes API from within a pod. So if we can find those, we can potentially go and grab the service account, and then we can authenticate to the API server and ask, who am I and what can I do? We can then enumerate our permissions. If we can get into another pod, we can then start to pivot around the infrastructure. This is the quintessential sort of canonical Kubernetes service misconfiguration, where people are able to exploit those jumps. In this case, So basically what we can do, instead of SSHing directly in, I will deploy another nefariously named container, escalate my privilege there, and try and demonstrate this via the back door, if you like. Okay. You can see who I am. Cool. Okay. Should probably explain what I've done there. So instead of, I basically jumped kind of back in from where I was on the previous run through this. So kube control, run, root, don't restart, image, lol, because we override it. Again, host PIDs, containers, Alpine, we're using the same NSenter hack, going with bin bash. This is my secret backdoor string. It's just setting up a load of environment context. And because there's no admission control, and at the end here, importantly, we've got security context privileged, I've just SSH'd onto the machine without using SSH. I've gone in with a kube control deployed, like I did with the previous attack, but just in a slightly more automated manner. Okay, let's see if I can get. So now what do I want? Not that. So let's go back to that case secrets file system dump. Let's take that whole thing, because I also don't. The joy of the portable home directory is that it can bounce through lots of different things, but I've got it set up here to bounce through assigned S3 buckets, and that also didn't seem to do what I wanted it to do, so I'm just going to copy the one thing in that I want. Okay, hopefully this is where the demo left off. All right, so as long as I'm on the node that I think I am, maybe not. So let's have a look at what's in that pod directory. Okay, so these are the representations of the pods on disk. Obviously, we've got to have these things in there so that we can debug appropriately. Let's try this command, ksecrets file system dump. Happy days. Okay, so what we can see here, we've got those ca.certs, the namespace, the token. Those 3 bits of information together give us access to the Kubernetes API server, and traditionally, as I say, we would bounce around using those specifically, but in this case, I happen to know what I'm looking for, so I will search specifically for AWS keys. Why might these be in a Kubernetes cluster? Well, potentially somebody is trying to auto-scale their nodes themselves, or they're pushing stuff to S3, or they're running Terraform. None of these are good reasons to use static credentials. There are high-quality workload identity integrations that use the properties of a pod to exchange for ephemeral tokens. We should never be hard-coding these strings anywhere these days. So what does that mean? I now have something with which I can potentially continue my escalation, my attack of the cluster. Okay. Sorry, that got a little bit meandering, but the point here is that these Temperfest mounts, the secrets for every pod, so all those Temperfest mounts that are mounted into the pods must exist on the host, because otherwise there's no way for them to be mounted into the container namespace. When the kubelet starts a pod, it asks the API server for, well, it's told which pod to pull, but then it asks the API server for things defined, like volume information, like secrets. The kubelet used to be able to pull secrets for anything. Now there's a combination of 2 plugins, the node authorizer and the RBAC node plugin, that mean the kubelet can only pull secrets for pods that it has been orchestrated to run. So that's the point. That's how we were able to find those secrets. There are some strange attacks you can do here. If you know that the workload that you want is running on a different node, you can denial of service it. And if that is removed from the pool because it runs out of resources somehow, then its pods get rescheduled. If you can also relabel yourself as a node, unless you use a specific string, and only a specific format of string is immune to relabeling attacks. There are some very nefarious edge cases there. Okay, so that was what we just did, enumerate the host. Don't multi-tenant along similar data classifications. These are the pivoting kittens of Kubernetes. Okay, we are almost into the final stage of cloud account takeover. Okay, so I think my slides haven't quite caught up with me there. Okay, no warehouses were harmed in the making of this supply chain fail. But this is what happens. Okay, so what are we going to try and do? We have now exfiltrated the key. We've exfiltrated the keys for an IAM account in AWS. If these are overprivileged, we will then be able to use them to elevate our own privilege and ideally find ourselves in a position where we can take over the cloud account. So what do we do by default in these situations? We run the AWS simple token service get caller identity call, and we hope that the name that comes back tells us something instructive, like cluster admin or God mode. Oh dear. This is a canary token, which means that the owner of this token has been alerted that something they hid around their infrastructure, waiting for somebody to break in and find, has just been used. This means probably the access I had will be terminated, the network around the cluster may just be dropped so that people can then perform forensics, get access to logs. The last line of defense should always be intrusion detection, but even intrusion detection can be turned off and circumvented. So control plane scatter these liberally all around our infrastructure and our laptops. You can also do this in your Kubernetes systems. In this case, we have an attacker, again, with that reverse shell, which would be up in the front end. Attacker gains remote code execution of front end pod. They would then look to enumerate the local network, to scan the visible horizon. They might do this just with nmapping, port scanning things. They might try and do it with a zone transfer or a weird DNS lookup, which various core OS versions, core DNS versions have been historically vulnerable to. As soon as, also we've named the service crypto wallet here, which is suitably tantalizing, one would hope. The point here is that as soon as anything hits that service, we can hook that up to our SIEM and we can light up like a Christmas tree because we shouldn't have pods scanning other pods in production. We should also have detection on for this. The container scanning and posture management tools will do some of this for you, but it is very easy to do with canary tokens and an Nginx as well. So what next? Well, Kubernetes is breachable in all sorts of fun and interesting ways. It is all things to all people, which from the one perspective is good. From the other, it is a almost unbounded set of permutations of complexity. These are some of the many ways that it can go wrong. The book goes into lots of detail. The pod treasure map, again, is the noisy way to attack, but a stealthy attacker will tiptoe through. Control plane are in the region doing stuff like this for fun and actually our day jobs too. We have an excellent penetration testing team. Threat modeling Kubernetes is our core skill. Deployments for regulated industries, banks, anything that is a little bit difficult. We have a team of bright and happy souls who enjoy doing this kind of thing. If it's in the book, we do it to some extent. And we'd be very happy to either deliver training or workshops in order to talk to stakeholders and demonstrate value. Thank you very much for your attention and patience.